Welcome to the video for skill number 76, graphing rational functions. I can transform rational functions and identify transformations from graphs and equations. This skill is going to focus on looking at an equation and figuring out all the features of a rational function and using that to graph the rational function. We'll start our notes on page 76A. And here I start by listing the key features that we want to look at. The first key feature is holes in the graph, and then we have asymptotes, both vertical and horizontal. There is also a slant asymptote, but we don't go into that in this class. Finally, there are the intercepts, the y-intercept and Xintercept. There's possibly more than one X-intercept, but there's only one Y-intercept, if there is one. Alright, we'll start by discussing holes. Holes in a function occur when the numerator and denominator share a common factor. So when we see a rational expression, our first thing that we should do is always factor it out, because the factored form is going to help us find all of these key features. So generally I'll be listing them in the factored form, assuming that you have already factored it down to the form represented. So in our first example we have x plus 1 times x plus 3 over x plus 2 times x plus 3. And this function has the term x plus 3 in both the numerator and the denominator. So we wind up getting a whole where x plus 3 equals 0. In other words, a whole at x equals negative 3. So the graph for this particular function looks something like what I've drawn here to the right, and what we have is at negative 3, so negative 1, negative 2, negative 3. Right here there's a hole in the graph. It's called a discontinuity. So the function is going to start way over here and slowly climb, and then at that hole it does not touch, and then it drops back down and continues upward like this. The other half looks like this. We'll get to the blue dashed line. It's a vertical asymptote, but for now we're just focusing on the hole. So I'm going to erase this and talk about the next function. Alright, for the second function, x minus 1 times x plus 7 over x plus 1 times x plus 7, we notice that we have x plus 7 in the numerator and the denominator, so we wind up having a whole at x equals negative 7. For this graph, it looks very similar in the sense that we have this vertical asymptote that it approaches, but the focus right now is just the whole, which occurs at negative 7. So we got negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, negative 7 is where the hole on the graph occurs. And finally, for the last one, we see that x minus 1 occurs in the numerator and the denominator, so the hole occurs at x equals 1. If I wanted a hole at, well, we'll say 2/5, maybe the best way to think of that is I might have x plus 1, x minus 3, and then because I want a hole at 2/5, I would have 5x minus 2 in the top and the bottom. So the way I could see that is 5x minus 2 equals 0, 5x equals 2, so the hole is at 2/5. We need to be able to look at these factored functions and find holes. The other type of discontinuity that we have is called a vertical asymptote. And vertical asymptotes in a function occur at all values which make the denominator equal to 0, excluding the holes. So in our first example, we have a hole at 1. So because it cancels out the top and the bottom, However, at the value x equals 3, we have a vertical asymptote. Looking back at this one, since we have the graph drawn, remember we had a hole at -7 right there, and then we're going to have a vertical asymptote at -1, and that's what this blue dashed line is. This example here, the x minus 3 is a hole, so we wind up having a vertical asymptote at x equals 5. We also have a hole at 0. So what we wind up, if we wanted to, we could say hole at x equals 0 and at x equals 3. Finally, in our last example, we see that no term in the denominator cancels, so we have 3 vertical asymptotes, one at 0, one at 3, and one at -5, because any one of these 3 values would set the denominator equal to 0. The next type of asymptote is the horizontal asymptote, and this occurs in a rational expression some of the time, but not always. It depends on the degree of the numerator and the denominator. So if the numerator degree is greater than the denominator, for example, if I had 5x to the 7th plus da 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 over 5x to the 6th plus da 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 da, the degree in the numerator is higher than the degree in the denominator. This would have no horizontal asymptotes. If the degree in the numerator is less, we'll say 3x to the 9th plus da 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 over 17x to the 12th. Notice the degree in the numerator is less than the degree in the denominator. Then we get a horizontal asymptote at y equals 0. And then finally, if we have a condition where the numerator degree is the same, 2x squared plus da 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 over 5x squared plus da 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 da, then the horizontal asymptote occurs at the leading coefficient of each. So we take the leading coefficient 2 and the leading coefficient of 5, so we would get a horizontal asymptote at 2/5. I've shown 3 examples below, and you'll notice that in the first one, the degree in the numerator is higher than the degree in the denominator, so there is no horizontal asymptote. In the second example, the degree in the numerator is less than the degree in the denominator. There is a horizontal asymptote at y equals 0. And then finally, in the last example, the degree in the numerator is the same as the degree in the denominator. So we get a horizontal asymptote at y equals the leading coefficients, so 3/2. We'll focus now on the y-intercepts of a function. So the y-intercepts of a function can be found by evaluating f of 0. So basically we plug 0 into our expression. So in the first example, we have 0 squared plus 2 times 0 minus 1 all over 0 squared plus 3, which gives us 0 plus 0 minus 1 over 0 plus 3, which is equal to -1/3. So we get a y-intercept at 0, -1/3. Our second example, we do the same thing. In factored form, we have 0 plus 7 times 0 minus 2 over 0 plus 1, which is equal to 7 times -2 over 1, which is -14. So we have a y-intercept at 0, -14. The last key feature of a graph is the x-intercepts. And x-intercepts, or zeros, of a rational function will occur at points where the numerator equals 0, provided that this does not conflict with holes or horizontal asymptotes. So in the first example, I've provided it in factored form, so what we can do is we can take a look and say that in this particular case, when x is negative 2, the numerator would be 0. So we have a x-intercept at negative 2. If x was negative 3, then we have a x-intercept at negative 3 comma 0. That's a typo. Let's fix that. Negative 3 comma 0. And finally, when x equals 1, we wind up having a x-intercept at 1 comma 0. All of these work because none of them are vertical asymptotes. There is no horizontal asymptote, and none of them are holes. So these all work as x-intercepts. The next example we have here, our x plus 3 cancels, so we don't have a x-intercept there because it would be a hole. We only get an x-intercept at x equals 1. So let's see how this plays out on our example here for the full problem. If we were to focus in on just this one and I asked you to graph it, what you could do is you could first say, well, we have a hole at x equals negative 3. We have a vertical asymptote at x equals negative 5. We have a horizontal asymptote at y equals 2, because our leading coefficients are 2 over 1. We have x-intercept at 1 comma 0, and we have a y-intercept at, let's see, we have 2 times 3 times negative 1. Remember, we're plugging a 0 in. And if we plug the 0 into the denominator, we wind up getting, let's get this pencil, 0 plus 3 and 0 plus 5. All total, we wind up getting negative 6 over 15. So we have a y-intercept at 0 comma negative 6 over 15. So the skill test, we will need to find all 5 of these features if they exist, and then we'll need to draw a graph of those 5 features. So the first thing I like to draw is a vertical asymptote. So we have a vertical asymptote at negative 5. 1, 2, 3, 4, 5. So there's our vertical asymptote. Then we have a horizontal asymptote at y equals 2. 1, 2. And then I like to plot the x-intercept and the y-intercept. So we have an x-intercept at 1, 0. So right there. And then we have the y-intercept at 0, negative 6/15. So somewhere right around there. Make it blue. Which means our curve probably does something like that. If we're going to adhere to the asymptotes, we cannot cross the asymptotes. Instead, we just get ever closer to them, but never cross them. And then over here on this side of the graph, we have 2 conditions. It can either curve down, fix that, there we go. It can either curve down like this or up like this. That way it doesn't cross the vertical asymptote and doesn't cross the horizontal. Well, if it curved down like this, we would get another x-intercept, which we do not have. So we know it has to be on this half. So it does something to that effect. And then the last thing we need to remember there was a hole, which was at -3. So 1, 2, 3, there is a hole right there. So we draw a circle. And we should be able to, well, I can't erase the line, but there's a hole right there at -3. So the worksheet should give us plenty of practice on finding these 5 features and using it to graph. Alright, the key ideas and concepts for this, we should be able to identify discontinuities, and that comes in either the form of a hole in the graph, or it comes in the form of a vertical asymptote in the graph. There's also sometimes horizontal asymptotes, so maybe there's a horizontal line here that the curves get ever close to. We should be able to find the zeros, which are the x-intercepts, and not all graphs have x-intercepts. Some won't have any at all. And then finally, we should also be able to find the y-intercepts. And similarly, not all graphs have y-intercepts. If we take a look at the function 1 over x, if we were to graph that, we would find that there is a horizontal asymptote at 0 and a vertical asymptote at 0, so the graph actually never crosses either axis, and so it has no x-intercept, no y-intercept. Alright, this is a very dense skill. I encourage you to practice this numerous times on the worksheet, and don't hesitate to come to me with questions. Alright, thank you.